Right now, millions of tons of solid rock are trying to crush the air out of this tunnel. The lithosphere does not tolerate voids. Every cavity opened in the Earth's crust is an insult to the geological equilibrium that existed before the first miner swung a pick, and the rock responds to that insult with relentless, patient, irresistible pressure. For 3,000 years, humanity has been fighting a silent war against lithostatic pressure, from wooden timbers that creak and split under impossible loads, to the massive hydraulic steel shields that hold back millions of tons of rock face while boring machines advance through it. The physics has not changed. The rock presses inward with a force proportional to the depth of the excavation and the density of the rock above. At 1 kilometer depth, that force exceeds 25 megapascals, enough to crush concrete, collapse steel, and compress solid rock itself. If the support structure fails for even a fraction of a second, the ground takes everything back. In this documentary, we trace 3,000 years of underground structural engineering, from the empirical timber props of the first miners to the AI-predicted rock burst of 2026, and reveal how humanity learned to hold the weight of the world above its head. How did ancient miners survive kilometers underground without modern physics? The answer is not that they did not understand the forces acting on them. It is that they understood those forces empirically, through the accumulated experience of everyone who had gone underground before them and come back, and everyone who had not. The creaking of a timber prop under increasing load. The subtle change in the sound of a tapped roof that signals loosening rock above. The pattern of small failures that precede a major collapse. This was the sensing system of ancient underground engineering. Human perception calibrated by generations of experience in environments where the penalty for miscalibration was instant death. In this documentary, we trace the claustrophobic evolution of deep underground stabilization, from the arched stone masonry of ancient mines that are still standing today, to the massive hydraulic steel shields of 2026 that hold back millions of tons of rock while boring machines advance through it. We reveal the structural secrets that allowed humans to open permanent voids in the planet's hostile crust, and show how 3,000 years of engineering intuition became the formal science of rock mechanics. Beneath your feet, right now, there is a world of extraordinary engineering. Caverns held open against millions of tons of pressure by geometry so precise that a deviation of centimeters would cause catastrophic collapse. Tunnels boring through water-saturated ground that would drown an unprotected excavation in seconds. Support systems so sophisticated that they monitor their own structural state in real time and predict failure hours before it occurs. For 3,000 years, humanity has been descending into the abyss, learning, through catastrophic failure and painful trial, how to make the planet's crust hold still long enough to be useful. From primitive timber props to today's high-technology steel skeletons, we are going into the abyss to see how primitive support methods evolved into the incredible science that prevents the ceiling from falling. 3,000 years of one question. How do you keep the rock above you from becoming the rock around you? The first underground engineers did not have a theory of rock mechanics. They had observations, accumulated, transmitted across those generations, encoded in practice rather than mathematics, about which underground situations were dangerous and which were survivable. The fundamental observation was simple: unsupported rock falls. The engineering response was equally simple: support the rock before it falls. The first support systems were the rock itself, natural pillars of unexcavated material left between adjacent working areas, carrying the weight of the overlying rock to the floor below. The pillar install method, still used in modified form in some mining operations today, divided the ore body into a grid of rooms separated by pillars, leaving enough material in the pillars to carry the roof load. The pillar dimensions were determined empirically: too slender, and the pillar fails under the load; too massive, and too much ore is left unmined. Generations of miners learned the correct ratio of pillar width to height for each rock type through the failures that occurred when the ratio was wrong. Timber provided the first active support system, a structure installed in the excavation that carried roof loads rather than relying on the unexcavated rock. The simplest timber support is the prop, a vertical post carrying a horizontal cap piece that bears against the roof. A timber prop transfers the roof load to the floor through the prop, bypassing the weak or fractured zone in the roof that might otherwise fall. The critical property of timber as a support material is its behavior under overload. It does not fail suddenly. As the load increases beyond the timber's elastic capacity, the wood fibers crush progressively. The prop shortens, audibly creaking and cracking, giving the miner warning that the roof load is increasing and retreat may be necessary. This acoustic warning system, the sound of timber under increasing load, was the primary safety mechanism of underground mining for 3,000 years. Ancient miners understood instinctively what took centuries to formalize mathematically. The arch is the most efficient geometry for resisting compressive loads. A circular or pointed arch transfers the vertical loads from the roof into compressive forces in the arch members, which are then carried to the abutments on either side. Stone, which is strong in compression but weak in tension, is the ideal arch material, and ancient miners who used arched stone masonry to line their tunnels created structures that are still standing today, while flat-roofed timber supported excavations of the same era collapsed centuries ago. The Roman mines at Rio Tinto in Spain, operating continuously for several centuries and producing silver and copper on an industrial scale, used arched stone masonry in their permanent access tunnels, combined with timber props and natural pillars in the working areas. The distinction between permanent infrastructure requiring durable support and temporary working areas requiring only sufficient support for the duration of mining is the same distinction that drives modern underground design. Permanent tunnels lined with concrete, temporary headings supported with timber or rock bolts. The Industrial Revolution transformed underground engineering by introducing two things simultaneously: deeper mines that encountered support conditions beyond the capacity of timber, and the mathematical tools to understand why timber was failing. Joseph Black's work on heat and pressure in the 1760s, combined with the growing body of empirical data from the expanding British coal mining industry, began to establish the quantitative relationship between depth, rock density, and the pressure acting on underground openings. The concept of lithostatic pressure, the vertical stress in the rock mass equal to the weight of the overlying rock column, gave engineers for the first time a number they could calculate and compare to the capacity of their support system. The immediate practical consequence was the recognition that at sufficient depth, timber could not carry the roof load. Cast iron segments, strong in compression, manufacturable to precise dimensions, and capable of carrying loads far beyond the capacity of any timber section, replaced timber in the permanent lining of deep mine shafts in the early 19th century. The cast iron tubbing system, flanged segments bolted together to form a complete circular ring, the ring itself acting as an arch to resist the radial pressure of the surrounding ground, was the first engineered underground lining system based on calculated structural principles rather than empirical tradition. The British method of underground construction, driving a small pilot tunnel ahead of the main excavation, supporting it with timber, then enlarging the excavation in stages while installing the permanent lining, was the systematic engineering response to the problem of working in ground too weak to stand unsupported for more than a few hours. By excavating small sections at a time and installing support immediately, the British method minimized the unsupported span at any moment during construction, keeping the roof load within the capacity of temporary timber support until permanent cast iron or brick lining was installed. The square-set timbering system, developed in the silver mines of Nevada in the 1860s, represented the most sophisticated timber support engineering ever developed. A three-dimensional framework of interlocking timber sets, each set consisting of a cap piece, two posts, and a sill piece, was assembled as mining advanced, creating a complete timber skeleton that supported the walls and roof of the excavation simultaneously. The square set could be extended indefinitely in 3 dimensions as mining progressed, the new sets connecting to the existing framework to create a continuous structure. In soft, unstable ore bodies where no system could maintain a working space, the square set made large-scale extraction possible, at the cost of enormous quantities of timber, and the constant maintenance required to replace props crushed by continuing ground movement. James Henry Greathead's tunneling shield, first used in the construction of the Tower subway under the Thames in 1869, and refined throughout the following decades, solved the problem that had defeated underground engineers since the first attempt to drive a tunnel through water-saturated ground. How do you excavate rock or soil that will not stand unsupported for even the time required to install a support system? The shield provided the answer by making the support system and the excavation tool the same device. A cylindrical steel shell, slightly larger than the finished tunnel diameter, was advanced into the ground by hydraulic rams pushing against the installed tunnel lining behind it. Workers excavated at the face within the protection of the shield. Cast iron lining segments were erected in the tail of the shield as it advanced. When a complete ring of segments was installed, the rams extended again, pushing the shield forward by 1 ring width. The ground was never unsupported. The shield occupied this being excavated, and the lining occupied the space the shield had passed through. The transition from passive static support to active structural lining, a lining that carries load rather than simply preventing collapse, came with the development of steel arch ribs in the early 20th century. A steel arch rib, a curved section of rolled steel installed transversely across a tunnel, bearing against the rock on both sides, acts as a structural arch, transferring the roof load into compressive forces in the rib and carrying them to the tunnel floor through the legs. Unlike a timber prop, a steel arch rib distributes load over a large area of roof rather than concentrating it at a point, reducing the stress in the rock at the support contact and preventing the local crushing that causes timber props to punch through soft rock. The new Austrian tunneling method, developed in the 1950s and 1960s by Ladislaus von Rabchewicz and refined through extensive application in alpine tunnel construction, represented a fundamental philosophical shift in underground engineering. Classical tunnel engineering tried to stop the rock from moving. Nat Nem recognized that in most rock masses, some movement is inevitable, and attempting to prevent it entirely requires support systems of impractical stiffness. Instead, Nat Nem allows controlled movement of the rock mass around the excavation. using the rock itself as the primary structural element by installing flexible support immediately after excavation that permits enough deformation to mobilize the natural arch in the rock while preventing uncontrolled collapse. The NATM support system, sprayed concrete applied immediately to the exposed rock surface, combined with rock bolts that anchor into the stable rock mass beyond the disturbed zone, creates a composite structure in which the rock and the support system work together. The concrete prevents surface raveling. The bolts tie the potentially unstable near-surface rock to the stable rock behind, creating a reinforced rock beam above the excavation that carries its own weight. The resin-grouted rock bolt is the most important innovation in underground structural engineering of the 20th century. A steel rod, threaded at one end and fitted with a resin cartridge at the other, is inserted into a drilled hole in the rock and rotated to break the resin cartridge and mix the two-component adhesive. As the resin cures, it bonds the bolt to the rock along its entire length, creating not a point support that bears against the rock surface, but a structural element embedded in the rock mass itself. The bolt places the potentially unstable near-surface rock in tension, pulling it toward the stable rock mass beyond the bolt anchorage, transforming a zone of loosened, potentially falling rock into a reinforced beam that supports itself. A pattern of rock bolts installed on a regular grid across the roof of an excavation creates a self-supporting rock beam with a thickness equal to the bolt length. The beam is reinforced in tension by the bolts, in the same way that steel reinforcement bars reinforce a concrete beam. The rock provides the compressive strength. The bolts provide the tensile resistance that concrete lacks, and rock also lacks when subjected to the bending that occurs as the roof tends to sag under its own weight. The longwall mining system, used in the majority of underground coal mining globally, represents the opposite engineering philosophy from the pillar install method. Instead of supporting the roof to prevent collapse, longwall mining allows the roof to collapse in a controlled manner behind the mining face, supporting only the immediate working area with massive hydraulic-powered supports. A longwall face is typically 200 to 400 meters wide. The coal is cut by a shearer traveling back and forth along the face. Immediately behind the shearer, hydraulic roof supports, each one a steel canopy supported by 2 or 4 hydraulic cylinders capable of exerting thousands of tons of force, advance automatically as the shearer passes, maintaining a supported working space. Behind the supports, the roof is allowed to collapse progressively into the mined-out void, the caving roof providing a natural pressure arch above the supported zone. By 2026, the digital intelligence of underground structural monitoring has reached a level that would have seemed impossible to the engineers of a generation earlier. Fiber optic strain sensors embedded in rock bolts monitor the load in each bolt continuously, reporting load changes in real time to a central monitoring system. Microseismic arrays, networks of sensitive geophones installed in boreholes around a mining area, detect the acoustic emissions from stressed rock at distances of hundreds of meters, locating stress concentrations and tracking their development over time. Machine learning systems trained on the acoustic signatures of rock bursts that have occurred can identify the precursor patterns in new data and provide warnings hours before a failure event. Warnings that allow personnel to be evacuated and equipment repositioned before the burst occurs. The structural engineering challenges of ultra-deep mining, mines extending 5 kilometers or more below the surface, represent the frontier of what rock mechanics currently understands and what support engineering can currently achieve. At 5 kilometers depth in hard rock, the lithostatic stress exceeds 130 megapascals, greater than the unconfined compressive strength of many rock types. The rock at this depth does not behave like a brittle solid. Under the combination of high confining pressure and elevated temperature, it behaves plastically, deforming continuously under load rather than failing suddenly. The excavation does not collapse. It slowly closes, the walls moving inward, the floor heaving upward, the roof descending, until the opening is consumed by the plastic flow of the surrounding rock. No conventional support system can prevent this. The forces involved exceed the capacity of any steel or concrete structure. The engineering response at ultra-deep levels is not to resist the rock movement, but to manage it, using high-elongation support systems that yield under increasing load rather than failing, maintaining the support function while allowing the rock to move. Yielding rock bolts, bolts designed to slide in their anchorage when the load exceeds a threshold, absorbing energy through friction rather than failing in tension, can survive rock movements of tens of centimeters that would break a conventional bolt. The same underground infrastructure being developed for ultra-deep mining is being repurposed for long-term storage of substances that must be isolated from the human environment for geological timescales. Deep geological repositories for high-level nuclear waste, excavated in stable rock formations at depths of 300 to 500 meters, apply the same structural engineering principles as deep mines, adapted for a design life measured in tens of thousands of years rather than the operational life of a mine. The underground spaces that humanity has learned to open and hold open against the planet's geological pressure are now being proposed as the locations for permanent human infrastructure. Data centers cooled by the stable thermal environment of the deep subsurface, research facilities operating in isolation from surface electromagnetic and seismic noise, and eventually permanent habitation spaces in deep rock that offer protection from the surface hazards of a warming and increasingly stressed planetary environment. 3,000 years ago, a miner in a copper mine in the Sinai Desert propped a timber post against a cracking roof and bought enough time to get the ore out before the ground came down. Today, a rock mechanics engineer at a desk in Johannesburg reviews a microseismic alert from 4 kilometers below the surface and initiates an evacuation before the rock burst occurs. The question they are both answering is identical. How do you keep the rock above you from becoming the rock around you? 3,000 years of engineering. The same question. Better answers, but the rock is not changed and it is not finished asking.